You may remember me mentioning that all stoichiometry problems are essentially the same at heart. And what I mean by that is you've got a completed balanced chemical equation that gives you ratios, and then you use those ratios to find out how much you can make. And then the steps end up being like, oh, you can compare stuff, blah, blah, blah. Well, sometimes a lot of words turn into a small problem, or not even that many words turn into a really small problem. I apologize for my super crooked line, but that's life. So let's look at some problems that have words, right? They look different, but they're still the same as what we need. I mentioned earlier in another video that like being able to do this, either one of this or whatever, you'll be able to do anything that is asked of you. So we've set up a template for how to answer anything. Yeah, we can get anything we need with the tools we have. It's just that sometimes we don't need all of that, and perhaps we can cut some corners. So I started out by writing some problems like you might see in a textbook, and various wordings and whatever, and I want us to take those words and turn them into something. And for each of these, I came up with the chemical equation, balanced chemical equation in advance, came up with the molar masses and everything else. And you'll notice over here I didn't even bother with those molar masses because I didn't want to waste my time. We didn't need them. So reading problems, like this is a huge mental hurdle. This is taking the numbers that we had in all these previous problems and applying them. And the key, and this is something I tell my students all the time, look for numbers, right? That's all I see. It's like the matrix to me. I just look for numbers. So in this problem, I'm looking for blah, 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 420 grams of sodium hydroxide. And sodium hydroxide's NaOH. I had to turn words into a formula. That's a really standard thing that they're going to ask you to do. So I have 420 grams of sodium hydroxide. Oh, I have, right? We're familiar with these words. So we've got 420 grams of sodium hydroxide. I gave the mass here as 40.0 grams per mole. And so we end up with 10.5 moles of NaOH. That is what we have, right? And in the back of your mind, you could be saying like, well, I'm used to seeing two numbers, but I only have one. So what am I going to do? Well, the answer is we're looking for the other number. All right, that's it. So a key word that you're going to look for then, we've exhausted our opportunity to look for numbers. The key words you're going to look for are things that you've seen in other problems. Masses, right? And then this word right here, which I feel is super important, right? We've been labeling things as what we have and what we need. So what we're asking for is what we need. That's how short this problem is. In fact, I'm going to stop talking and just do it. Oops. We have one number. We can find one thing for starters. We know that for every 3 moles of sodium hydroxide, we have 1 mole of AlBr3. That's from our balanced chemical equation. So we end up with, in this case, 3.50 moles of AlBr3. Right? We want to know how much we needed. That is how much we needed. But we didn't want moles, we want a mass. So let's add that half a step here. We want a mass, and we'll multiply by molar mass to get that. I gave you the molar mass as 266.68. And in this particular case, you end up with 933.4 grams of the aluminum bromide needed. And that's like a pretty real-world type of scenario, is I've got this much of one thing, how much of the other thing am I going to need to use it up? And that's it. All right, that is our answer. So again, we had the tools in place, like here's our steps. Compare the reactants to each other to find limiting and excess. We only had one number. We compared to find what we need, and we were done. Yeah. I want to glance at this one here, and then we'll jump back to this, because I want to look at this as a huge chunk of words and how it relates to the whole problem, and then we can look at the smaller version, how we could have made that a shortcut. So I guess right here might be a good place for our steps. Hydrogen gas is blah, 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 blah. You can read it. My goal here is I'm going to look for numbers, hydrogen gas, temperatures. Do you remember temperature coming into play in any of our other problems? No. So I don't think it's going to come into play here, right? 10 grams. Grams sounds familiar, right? Grams is a mass in this case, of each reactant. That sounds like what we is present. That's what we have. So let's start with that. We have 10 grams of each reactant, so that's 10 grams, 10.0 grams of hydrogen gas. And, oops, jeez, I'm going to just scrap that. 10.0 grams of hydrogen and 10.0 grams of bromine. We can't work in grams because the balanced chemical equation gives us a mole ratio, so I'm going to divide by the molar masses. In fact, let me do that in green. I'm going to divide by the molar masses, 2.02 grams per mole and 159.80 grams per mole. And that's going to get us what we have, right? And they told us we have that. For the hydrogen, we have, let me move over, there it is, 4.95 moles of hydrogen. And for the bromine, we have a much smaller number because it's got a much higher mass, and that is 0.0626 moles of bromine. That's what we have. We're going to do a quick stoichiometric comparison to find out what we need. Everything after the first box comes from the balanced chemical equation. We're still on this step right here. From the balanced chemical equation, we see for every 1 mole of H2, we need 1 mole of bromine. And we end up with needing 4.95 moles of bromine, which we certainly don't have, and 0.0626 moles of hydrogen, which we way more than have. So in this first step, we're asked to identify the limiting reactant and the excess reactant. I have 4.95 and I need 0.06. That is our excess reactant by far. I have way too much. I have 0.0 and I need 5. That's not even close. That's going to limit us considerably. So we did this step just like we always would, and now we need to find amount excess because, look at these words here. What mass of which reactant remains after the reaction has reached completion? Key word here. Which reactant remains, right? Means it has not been used, so that has to be our excess. We want an amount excess. And the good news is we have that tool in our toolbox. We've been doing it every single time. To get our amount excess, we're going to take what we have minus what we need of the excess. And in this case, 4.95 moles of hydrogen minus our 0.0626 moles. And we end up with there 4.89 moles of hydrogen excess. And just to always add that 1/2 a level of difficulty, let's turn that into a mass because it says what mass, right? And this is reactant remains. I guess I didn't mention that earlier. How do we know we're not coming up with a product? Because it says mass of reactant left over. That's how that translates, mass of reactant left over. We're going to multiply by 2.02 grams per mole, and we'll end up with 9.87 grams of extra hydrogen. Right, and that excess means like remains, right, or left over. And that is our answer right there. All right, now we jump over to this problem. Again, like this is our process. We have this skeleton laid out. It's just that sometimes you don't need that whole skeleton, okay? Good, that'll actually fit quite nicely right there. Let's look at this. That's an essay, right? Like when I'm going over example problems in class or when kids have a question in class and they'll be like, oh, I need some help on number 8. And then I look at it and then I just put my head down because like that's a lot of words. Again, my strategy, look for numbers. That's some amount of something, blah, 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 blah. That's some amount of something, blah, 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 blah. That is some amount of something, and then I want a percent yield, which is a word that I have heard of before, right? That's literally how I handle these type of problems. All the words are very often there just to trick you. The basic things that we're going to have to be given is some starting amounts and perhaps an actual yield. And since we're looking for a percent yield, we have to have that. So I'm going to look at this in the skeleton of this whole thing, and I'll go back maybe in pink or something and highlight how we could have made it much faster. And you don't have to. That's the thing. We have the tools to come up with everything we need, and sometimes we don't need everything. Let's give it a try. In this particular case, we are given some amounts. We're given 210 grams of chlorine trifluoride. Again, one of the problems might be coming up with a chemical reaction, and there would have been more words possibly to do that, but I got tired of writing. So we've got 210 grams of chlorine trifluoride, ClF3, okay? And we've got 123 grams of ammonia, which is NH3. Those are gram amounts. We need to turn those into mole amounts so that we can do this step right here, which is comparing. I calculated the molar mass as 92.45 grams per mole and 17.04 grams per mole. This is going to tell us what we have, because I want to know what we need. That is what's going to allow us to find our limiting reactant and our excess reactant. In this particular case, the 210 over 92 ends up being, I'm sorry, I lost my problem here. The 210 over 92 ends up being 2.27 moles. 2.27 moles ClF3. And the 123 over 17 ends up being 7.22 moles of our ammonia. Again, we have to get moles because the balanced chemical equation gives us a mole ratio. And as you'll see with later problems like solution stoichiometry or gases or whatever, this step remains the same. What changes is what's right there in the beginning. All right, balanced chemical equation, 2 moles of ClF3 for every 2 moles of NH3. And boy, is that convenient. Again, as we're looking back at some strategies we had before, I'm supposed to have the same amount. It's a 2-to-2 ratio. I have way more NH3. NH3 is my excess reactant. Again, you don't have to do that, but in the big picture, you can start thinking about things like that, right? Or in this, actually not that problem, but in this problem right here, I needed a 1-to-1 ratio. I needed the same amount. I had way more H2. H2 ended up being the excess reactant. So you can start looking at that if you are so inclined, but you don't have to. We've got this tool here that you can just blindly follow. 2.27 moles of NH3 and 7.22 moles of ClF3. We've identified our limiting reactant and our excess reactant. Have 2, need 7. Don't have enough. That's our limiting reactant. Have 7, need 2. We've got way too much. That's our excess reactant. Yeah? And so we've done this step. We don't need to find an amount excess, but I'm just going to pretend we're doing everything just like we've done in previous problems. And like I said, I'll go back and highlight so that we can see what I could have done. We're going to get an amount excess. I'll just make some room for myself there. And I know some of you are saying, we don't have to do all that. That's fine. Why are you watching this video, right? We're going to do the whole thing and go back and highlight the minimum we could have done. Have minus need, 7.22 moles of our ammonia minus 2.27 moles of our ammonia. So we end up with, in this case, 4.95 moles of our NH3 excess. And that's moles, like we've been going through this process, so I'm just going to go through all the motions again. Multiply by molar mass, we get 17.04 grams per mole, and this gives us 84.3 grams of ammonia excess. All right, that is that step. We're used to it. and now we're going to get a theoretical yield. We have 3 products, so there's going to be 3 values for our theoretical yield. The theoretical yield is based on our limiting reactant, so in this case we have 2.27 moles of ClF3. And for the limiting reactant, we're going to compare it to our products. And our limiting reactant, 2 moles of ClF3. And now I need to get maybe color creative, and we'll work our way down here. I've got 1 mole of N2. And so that's going to get me, let's see, 1.14 moles of nitrogen. And we can multiply by our molar mass to get a mass times 28.02 grams per mole. And that's going to give us 31.8 grams of N2. This is part of our theoretical yield here. And we also have our HF, so 6 moles of HF, which gives us 6.81 moles of HF as a theoretical yield. And we'll multiply by the 17.04 grams per mole, and that'll give us 136.4 grams of HF. And then we need to find out about our chlorine, and there's 1 mole of chlorine, and that gives us then half of that, so 1.14 moles of chlorine, multiplied by its molar mass, 70.90, and we end up with 80.5 grams of chlorine. So this right here is our theoretical yield. We're not asked for any of that, per se. We're asked for a percent yield, right? That's our main goal in the end. So we can check things like, we're not asked for it, right? But let's check and make sure. Our initial mass should be our final mass. And in the beginning we had 210 plus 123, and in the end we had 84.3 and 31.8 and 136.4 and 80.5. All right, and it looks like that does check out for us right there as 333 grams on both sides, or close enough anyway. And we'll move on to percent yield, right? This is something we've calculated previously. Percent yield is supposed to be the actual over the theoretical times 100. So percent yield is supposed to be the actual over the theoretical times 100. In this particular case, the actual yield is given as 107.4. And as you look at this, it says the presence from the experiment. So we have to imply that that's an actual yield. It's from the actual experiment that's in a lab, which was our basis for an actual yield. So we got 107.4 grams of HF. And I need to know that's the HF because I've got 3 different yields that I could work with here, but I need that 136.4 grams of HF times 100. Okay? That gives us 78.7, approximately 78.7% yield, which, by the way, was the only number we technically needed, but we had to get at least some of this to get it. So this right here is our answer. That's what we were looking for at this step right here. We can come up with some actual yields of the other reactants and budget our space accordingly. We know that percent yield is actual over theoretical times 100, so our actual yield has to be our percent over 100 times our theoretical. And in this case, we've got two theoretical yields, and I'm just going to cut some corners here. That's 0.787 times, we'll say, 31.8 grams of nitrogen, and 0.787 times 80.5 grams of chlorine. All right, and that all managed to fit on the screen. That should give us 25 grams of nitrogen as an actual yield and 63.4 grams of chlorine as an actual yield. So this is everything we've asked for in all these previous problems like this. And the question is, we were only asked for a % yield. How much could we have cut out? Well, you have to know your limiting reactant and your excess reactant. So this step right here we couldn't have escaped. We technically could have said to ourselves, I need the same amount of those. I don't have the same amount of those. This is my excess. So bare minimum, you probably could have done this step right here after doing this work right here. And you got to have a completed and balanced chemical equation. We didn't need this. We didn't need all of this. For our theoretical yield, you needed to take the moles of ClF3, and we were only worried about the HF. So I could have done just that right there, and I could have just had these numbers here, okay? And then to get our % yield, we have to do this step right here to get the thing we need. So this gives us the tools to find anything we might need. It will always be able to give us everything we need, but sometimes you don't need to do all of it. And with some practice, you can cut out steps. This was our step 1, 2, 3, and 4, more or less. All right, so the stuff I highlighted in pink is the bare minimum that could have been done to do this, which is a lot less than what we did. But by doing the amount excess, we were able to check and make sure we did it right, and we can get an actual yield of the other products if we needed to.